we're going to come up with a formula so we don't have to keep finding these equations of tangents to the curves and so forth and finding where their x-intercept is. We'll just do it once with a general one and then have a formula. But the idea is we start with an x1, we go find the function there, so we find this point x1 f of x1, we compute the tangent to the curve at that point, we follow that down to its x-intercept. Then we repeat the process. We put that in the function and we find its function value. We find a tangent to the curve at that point. We follow it down to its x-intercept. Repeat and so forth till we narrow in on the root. So to find the equation of the tangent to the curve, of course we will start with point slope formula, but let's use our notation, x1 for x and f of x1 for y, and we will solve this for y. We will also replace the slope with the derivative at x1. If we wanted to figure out where this crossed the x-axis, it would be where this y value was 0. So we could put it equal to 0. Then we could solve this by moving this term to the other side, dividing by this term, and then adding the x sub 1. So if we move this over, it would be negative f of x minus 1 divided by the derivative at x minus 1, and then what we would have left is x2 minus x1 here, and so we could move the x1 over. So this would tell us how to get x2 when we had x1, the function at x1, and the derivative at x1 without having to officially think of the tangent to the curve, although that is what we did to get here. Well, then if we wanted x3, we could take x2 minus the function at x2 divided by the derivative at x2. And if we wanted x4, continue, so we could generalize this. So to use Newton's method, here is a formula derived from looking at the tangent to the curve and finding its x-intercept. If we want any new approximate for an x value, we're going to take the one in front and then subtract the function at that x value divided by the derivative at that x value. And that will give us these various x-intercepts that will narrow in on this root. If the numbers xn that we're getting, because we're getting x sub 1, x sub 2, x sub 3, become closer and closer and closer to the root as n becomes large, we say that the sequence that we're generating by getting x1, 2, and 3 converges to r. We write the limit as n approaches infinity of x sub n equal r. So if we can keep going in on this closer and closer and closer, so x1, 2, 3, 4, dot, dot, dot to infinity, then we will have our root. So our procedure for Newton's method, we're going to guess a first approximation to the solution, f of x equals 0, and looking at a graph might help us see what might be reasonable to guess. Then we're going to get a first approximation, a second, and so forth by taking what we get and then substituting that in to get another one. You can see that this would very easily transfer over to a computer program with a loop, these iterations that keep completing. This is a way they program computers to find these roots, because you take out what you get and then you apply that with this formula again and you get the next approximate, and we can keep going with this. So if we had done that and kept going with the one where we were looking to find the square root of 2, just to show you here, if we would have started with 1, we got 1.5, and we got 1.41667, which actually has 3 correct digits. The error is quite small. If we would have done that even one more time, look how small our error is. We have accuracy to 5 digits. So it depends on what you start with and what your function is, but very often Newton's method converges very quickly. So let's see what we could do to find the coordinate of a point of the curve y equals x cubed minus x, where it crosses a horizontal line y equal 1. First, we'd want to express f of x equaling 0, and what we were interested in was when x cubed minus x equaled 1, because where they crossed each other, so then we could move this over and have it look like this. Now we would need to figure out some values that may be close to the root, and when we look at this function, if we put 1 in the function, you see we get out negative 1, and if we put 2 in the function, 8 minus 2 is 6, minus 1 is 5. So did we find a place where there's a root between these? Yes. How do we know that? The intermediate value theorem. Remember what the intermediate value theorem said. Here we have a value at 1, the function is negative 1, and at 2 to the function is 5, and if we have a continuous function, which we do, it's a polynomial, there is no way we can go from a negative function value to a positive without somewhere going through 0. So we know that somewhere between 1 and 2 there is a root. Let's look at the graph here, and you can see that it does in fact cross somewhere between 1 and 2. So we could start with Newton's method, and we could let our first choice be 1. We know that the function value at 1 is -1, and we could find the derivative of this function. F prime of x is going to be 3x squared minus 1. So if we evaluate this at 1, we get 2. So our slope is 2. We could find this tangent, but each time sort of doing this process is not what we want to do as far as finding the tangent and so forth. We're going to want to go to that formula that we came up with, which said to get any x, we're going to take the x in front, subtract the function value at x minus the derivative of that function at x. Typically when you do these, you're going to be using a calculator or a computer because you're going to kind of keep going, and whatever you get out, you're going to use it as your input for your next one. So I'm actually going to pull up a calculator and show you how I may do this on a calculator that can use the answer from the function above. So the calculator I happen to have on the computer is a grapher, but we're not going to use the graphing capabilities. If you have any calculator that can remember the answer, you can do it this way, and if not, most of them have some kind of a store, and you can use it as the store and then pull it up and then save it and then repeat this process. So essentially here is our formula. We're going to start with 1, so I'm just going to put that in so that that's stored as the answer. And then what I'm going to want to do, if I do second answer here, it brings up the answer because I'm going to want the x that I have, and then minus, and then I need the function at this x, and the function here is x cubed minus x minus 1. So I'm going to do second answer and make that cubed minus, use that answer again, and then minus 1. And I actually am going to need that in parentheses because all of that should then be divided by this other piece. So I need to insert a parenthesis here. So there's our ending parenthesis. And then we're going to divide that by, so I'm going to need a parenthesis again. So the denominator is the derivative at this value. The derivative is 3x squared minus 1. So I'm going to put in 3, pull up the value for the answer, and square it, and then subtract 1. Now this is going to compute for me my new x-intercept then, had I plugged in x1, followed the tangent to the curve down to the x-intercept. And it looks like I'm going to get 1.5. So I started at x1 equals 1, and after applying Newton's method once, I get 1.5. So my x2 equals 1.5. Now the reason I've bothered to put it in the calculator is because now I can actually repeat this. If I put all of that in there again, but it now uses 1.5, it's going to compute that same thing but with my new x value. You can see how if you programmed a computer how this would work very nicely. So my next approximation is 1.3478, so we'll say 1.35. So my x3 is 1.35, and I could continue this very same procedure, just simply repeating each time, and it's just working this formula each time, and I could come up with various approximates. So let's have a look here and see essentially what we found. So we started with 1. We followed it down, found the function value. We used Newton's method to essentially follow the tangent to the new x-intercept, which was 1.5. We put that in the function using that formula we derived for Newton's method. We then found the next value, which was 1.3478. We could continue to approximate this root. You can see that this actually converges very quickly to the root. If we started with 1, we get 1.5, but as we move along here, these are the various pieces that would be components for computing the new x values from the previous, but it very quickly converges. We can see that as we do the fifth one here, that we are not changing any numbers from the fourth one, and that's kind of when you'd know you'd be done out to this many decimal places for accuracy. Does not take a lot. If you were programming a computer and having these loops, you wouldn't have to do very many loops before you've got amazing accuracy. Now, it turns out on this one, if we would have picked any starting value that was to the right of 1 over square root of 3, it would lead to the root as we followed this. But if we would pick something over here and we find this, we could be led other places. So there's a lot of cautions for Newton's method, both for starting values and for if you're trying to program this or work on this to see if it converges. Here's an example where we could have started over here, come down and found the function, followed the tangent, converged very quickly. We could have started over here, found the function, followed the tangent, and converged very quickly. So sometimes it's not a big deal where you start and you end up in a great place. Here is a time where we'd be in complete trouble, because if we tried to start right here, when we go to find the function value and we find the tangent is horizontal. If you followed a horizontal, you are never going to get an x-intercept because it's parallel to the x-axis and you would be in trouble. So the method is not going to work if the x value you choose is a place where there is a local maximum or minimum, because it's going to just then follow a horizontal line forever. Another interesting thing that might happen is we might pick this value, we may go up and find the tangent, follow it down, plug that in the function, find the tangent, and we may end up further from the root. We may end up out here in La La Land, and so it's not always a guarantee that picking something close to the root is going to converge to the root. Another issue we might have is we might pick this value. We'll go down and find the function value and then follow the tangent and then substitute that in the curve and then follow the tangent and then substitute that in the curve and then follow the tangent, and then you get it. This one is going to just cycle, and you could have a function that this could happen, and so we've got to be careful as we're trying to use this method, watching for some of these issues. You may start with some value, follow the tangent, and figure you were going to narrow in on this root, and you may end up at a different root. So depending on what the function looks like and what the tangent does, you may end up somewhere you hadn't planned on. Here's another example, and it doesn't mean because you necessarily started near the root that that's the one you find. So if we start here and we go find the function and we follow the tangent, and we go find the function and we follow the tangent, and we keep doing that, we end up converging to this root, and we thought we were going to find this root because we started clear over here on the other side of this root, but we ended up clear over there. So be aware that Newton's method, we need to watch what's going on so we can then figure out what's going on, and it's helpful to look at some kind of a graph or sketch as we are doing this.